Okay, now in this video, let's try to make something interesting. We are going to move a dog in Gazebo Sim. We are going to animate it moving. It will follow points in Gazebo Sim. Okay, let's try and understand how to make it happen. Although there is something called actor that already exists as a tag in Gazebo. If you go onto this actor, there are already many of them, and there are options to put waypoints on them as well. But in this video, we try to use our own custom actor that would be a dog, and we'll understand how to make it work in Gazebo Sim. Okay, I want to first show you how this animation thing works, like how it is being designed, because I've designed it by myself, right? Not the entire design, but I've designed the animation part of it. So if you go inside Blender, this is the scene that I animated it. I downloaded it from some open source, and then I'm animating it. So let me close this doc. So if you see, these are the bones that actually what helps you to create animations. So if I turn this off and just play the animation. So see, this is the animation that we are going to use. And what happens when with this, what is going to happen? Dog is going to stay at one place and it is going to do like this. But the logic is what it happens, because we are going to apply some position changes, it will look like a moving one with the some linear velocity we are going to apply. So it will look like this, that it's, although it's moving in one place, but it will look like it's going like this. Okay, so let's try and understand how it works. First of all, if you want to download this Blender file, and if you want to make your own modeler and design any of your one thing, then you can do it in Blender. The only thing is that once your design is ready, you need to export it as DAE file. Only DAE is supported for this actor plugin. Okay, this is by default actor plugin is there in Gazebo. We are just going to put waypoints onto it by using our own code to make it work. Okay, so this is the thing, and let's jump into the presentation and understand how this logic actually works. So what happens, suppose this is an animal or any other actor, all the waypoint following logic works like this. So basically what are we have only one way to control is using position, right? So we'll understand how to use this position logic, and we'll apply a linear velocity so that those position keeps on changing constantly. Okay, so if you see this animation, what happens, the first thing that it happened, it turned on to this, because it has to head on to the direction where the waypoint is. So these are two waypoints and it's moving from this direction. So first it has to change its heading towards that, then it slowly moves, like it slowly changes its position, and then again it's reached this waypoint, then again it's going to do this, and then its orientation got changed. From here the orientation got changed depending on the waypoint that's next on it, and then again it slowly moves by gradually moving from one point to different, gradually changing its position from one position to different, like this. So now I hope this logic is clear, and this is animation that works around it, that the dog animation that's standing on it, and we just animate the motion of it moving from one point to another. This is the same logic that we applied on the dog plugin as well to make it work. So let's try and understand how code wise it actually works. Okay, so if you see, this animal or any actor plugin has just two things. One is pose, that will get you the current pose, and this trajectory pose is the pose that it's currently following in the trajectory. Okay, so if you want to control any of your joint, you need to control this trajectory pose. Okay, now let's see this. Okay, now let's try and understand the code, what it is doing. So basically I'm using the wrapper class of actor. In the code I've also put the basic way of using direct ECM to make it work, but here I'm using wrapper class. It's fine if you understand what the wrapper class is doing and it is not causing of you any problem, then you can use wrapper. I'm not completely against wrapper class. It's just that I want you to understand that what is the code, what it is doing before using wrapper classes, or directly use the entity component manager process of controlling any component. Okay, so what it does, it first read the pose, and at this point this animal is not in the world frame, it's in the local frame. We need to move it from local to world frame so that we can do things on the world frame, because we know the position of this in world frame, not in the local frame. That's why we are moving from here. We just firstly read the pose of this returns us this position value, whatever the value inside is there. then we make it as the origin, then we read the trajectory is basically this pose. So we read this pose and then we read the trajectory pose as well. So this is actually local, and this origin is at this pose, this origin pose, this is in world frame and this is in local frame. So multiplying them, we are going to convert it into world frame. So then using this trajectory pose, we are going to get the current pose of the animal or whatever actor you're using it's attached to, and then we just get it data, and at the end we multiply both of those values to get this trajectory pose in world frame. So now from local we made it to world frame, and now it will be easy for us to do all calculation because we already had this waypoints in world frames. Okay, so it would be much easier for us to do those calculations. Now once we have the waypoint, next is we need to calculate the distance. How we calculate the distance? Because the point where it is standing and the point this over here, both by doing minus. So basically it's a vector multiple, it's a vector addition and subtraction. This is vector subtraction. So when you're doing like this, so basically this is the world pose that we got from here, and this world pose is from the target pose. Target world is basically, this is the target world. So this is the target world, this is the target world, and minus, putting minus over there, this is a vector addition subtraction. Okay, so this is doing vector subtraction. That means from this point to this point we are drawing a vector, and that vector value is dir. Okay, and this is the position vector, and then we make z to 0 because we are just going to deal in xy plane and we don't need z. And then using this length calculation, length distance, basically will be able to get the distance of this. What is the distance between this point and this point? This will help us to find something. So for example, if the distance is so close, like it is so close, then that means the waypoint, the actor has reached this point, then we are going to switch to next waypoint. So if there is a waypoint over here, then we'll switch to that. But if it is not there, or if distance is extremely high, like for example 10 to the power 9, that's very high, then we are going to convert it into a unit vector. Instead of finding the distance, we convert into a unit vector that it just has direction, right? So we are going to do that. And if you see actually what it is representing over here, so if you see this correctly, so this point pt, that's basically somewhere over here where the animal is standing at present, this is the point P, and from here we trying to get this vector minus V. So this is this vector dir, this is from target minus the current position, and this is all done in world frame. Okay, so these are both on the world frame. Next step is, once we get the distance, now we are going to, as I told you, we are going to have a step, small step. We are going to take small step over here, like we are going to take this step, even it's going to be taller than, but this is for explanation, this small steps. And how this comes, basically this comes from dt. Delta t is the time that's every time a plugin runs, so we get a fixed time, like let's say it can be 0.01, 0.001, or some small value, very small value. If you multiply time and speed, what you get distance, right? So this step is basically a distance. So here we are using this information to get dt, we are converting it into a particular form. Now using this we get the distance. Now we got the distance, how much distance we have to move in each step. Now we are going to move this animal from here to here. We'll see how to do that. I'm explaining you code over here because with this animation it would be easier for us to understand. And now, although it just moved like this, but it's not moving at this present, at the end it is going to move, but for explanation I put it over there. So this step, as we discussed, it is just a distance, and we are multiplying these two values. This is dot multiplication, these are vectors, and this is going to get the world position of this. So basically this was the world position at P. Now this has moved to this point, or whatever this point, then it is the world position of this. World dot pose is basically the position of this right now. So using this vector, so we are multiplying the step to this dir vector so that we can get this current position. Okay, and for the world, as we wanted this target position, plus we adding some z offset, because what happens, for example, if your actor is like this, then what happens, sometimes there is a z offset in the actor. So to handle that thing out, so that at every point whenever the actor comes in, we have it like this, instead it is standing on the ground, so we have this z offset. So based on how much value we want, we can able to make it touch the ground, so that this animation will look good. This is just for that purpose. Okay, so now you got your pose, world pose, where you want to move it. Now we have this, now we have to get the angle as well. How we get the angle? So to get the angle, it's very simple. For your, you do this tan inverse, this tan inverse of y by x. So this is what's done over here, so it gets you the inverse, and we want it in robotics. Generally we use this quaternion, and even Gazebo Sim is going to accept all of your values in quaternion, so that's why we are converting into a quaternion form. And also we are adding an y offset over here. Why? Because what happens sometime, so if your actor is like this, it is moving in this direction, it is moving in this direction, but the actor is facing as this, so this would be an offset, right? Otherwise what will happen, even actor is like this and it is facing this side and it is moving this, so the animation and the face of the actor is not going to match. To make it match, what we do, we apply this yaw offset, so that the actor that's looking at this direction now turns into this direction, so this turns from here to here. Okay, maybe let's say 90 degree or whatever it is, so it is turning from here. So that's why we are multiplying a constant value, and it comes from the sdf file when we are loading it. Okay, so we are adding some values on z, we are also adding an offset on y, so that our model, the animation of moving looks good. It doesn't look odd, like it is doing lag over here but it's moving like this. I will show you those sort of error as well when we start the simulation. So this is the rotation you got. Then once your everything is done, now you have it in the world pose. So this entire pose is in the world frame. Now the problem is that we want to send it to trajectory, and trajectory is in local frame. It is in local frame, right? How will it make it happen from world to local? We need to inverse multiply it. So once we get this entire world trajectory, then in the first, if you remember what we do, we reverse this up so that we can add this on the world. Now we multiply world again with inverse of the origin, so that we can get back this trajectory command. So basically we are moving back from world to local frame to get trajectory. Okay, now we got this trajectory. Now it's very simple. With this set trajectory pose, in this ECM and trajectory command, we set this trajectory pose of this. So this is the wrapper classes I'm using. I've on the code I've also put with comments the normal standard component method. You can use that as well, or use this. Not a problem until and unless you understand how the code works. Now this is ready. What else we need to do here? If you remember, because this we are sending the actor position, it's very essential that we update, we set change, and we notify that this actor, the entity, this related component of this entity, this component is being updated. So if you remember, we did it in light when we are doing this. Same thing we are doing here, so that if by chance the entity component manager misses it to update, this will make sure the sets change will force it to update those values, so that we are going to get this animation. Otherwise what will happen, this animation may not work. Okay, so if you want to try it out, just comment this line and you will see animation stop working. So now the actual code, and I will show you some things in the code. So if you see now, this is the actor plugin, and this is pure Gazebo plugin, but still you can use with ROS workspace. It doesn't matter really, it's the same thing. It's just that we are not going to add any rows onto it while building it up. So this is exactly the same plugin. Then we are using pre-update only because we want to write it onto the trajectory. Then this entity and pre-update, everything is common. Now just we added up the list of waypoints that we want to, and we for this is current waypoint and this is last. For printing this purpose we have this chronicle rate. Okay, and your offset as we just discussed and z offset. And if we go on to the main code, first let me show you where what happens with this. So if you're seeing this SDF file, if you go over here, just go down. What we are doing on this file is we are including this model. Let's see the model first. So model is in the model folder in Gazebo ROS modeler folder. If you go onto the modeler folder, you will find this doc world, and on this you will find this .sdf file. So it's exactly same as it was there in Gazebo Classic, and now we are using this actor tag to load our model, and we are setting it an initial port. Then this is the skin file and this is the animation file. It's the both are same, just we are using the same DAE file. And the scale parameter is there but it doesn't work, so make sure that you remember. And it is not going to affect because this interpolation about x is not going to do any effect, because by code we are going to change this value up, so this won't have any effect. So this is the model file. Basically it's an actor that's being attached. Now on the include file, it just includes that SDF file, the model file over here. And on the plugin we are using this plugin, and these are the list of waypoints. This 4 waypoint, it's going to loop within this 4 waypoints. So 1 to 4 it's going to loop around, and this is a position and orientation, roll pitch yaw, and sorry, XYZ and roll pitch yaw. These are the values that you can set it up to make it work. And then here we are setting up a speed that we wanted to move with. So on this speed, and then your offset that we just discussed, and the z offset, so that it doesn't look odd, and we are able to control other parameters so that it looks like moving. Okay, now let's go on to the code. C++ code. Here we are using this configuration, and because this entity is directly attached, we can directly get the entity directly from here, because this plugin is directly attached to this model, right? So that's what I'm doing. I'm directly getting the entity to my actor entity. Or the other way would be, you can use this find actor each method, or there are many other methods that we discuss. You can use any of those over here. I haven't mentioned, but you can use any of those over here. And then what comes now, this, okay, one more important thing, I'm using this component to make sure that if this returns value, if you do not have an actor component attached to it, then it's going to return value and it is going to fail. Why? Because we want this plugin to only attach with the actor one, right? The actor tag over here. So basically with only the actor component. If it doesn't have the actor component, then it should not be attaching. For that, check it is there. Now we are using something new over here, just SDF file element. So this is way of finding the element, and it will get you a list of element one by one. So it's very easy, nothing very difficult to understand. So this is the name, and all the names are in waypoint. It's not like 1 2 3 4, it's all waypoints. So it is going to read one by one all of them, and it is going to give us the element value, and we are going to push it back on the waypoint list. So this is a vector. On this, it is going to just push all the values, and all these are post 3D. That means XYZ and roll pitch, all the 6 values are being added on the waypoint. Although we don't use them, but all the 6 are added up. Then with speed parameter, then same, it makes sure that if there is no waypoint, that this plugin is going to give us an error. Your offset, jet offset, and then we initialize. Then we go on to the pre-update, and we first check if waypoints are there. If it is there, then this is just for printing purposes. It doesn't do anything other than this. It just calculates the current time, and it runs at 1 hertz. Because of that, this logic is written over here to make it work. Print at 1 hertz. It should not print it randomly. Because of that is there, nothing special. Then here come the main code that we were just discussing. It checks if it gets the, and it puts the entity to get the actor class out of it. That basically the object, this is an object of the actor class. Okay, then using this we validate if if there is an actor on it or not. If there is an actor, then we can proceed. Or the other way to do it with ECM is basically use the component and you check if there is an actor component or not. If it is not there, then the same logic that I've added on, you can use this as well, or you can use this wrapper class. So it validates everything is there same, then it does the post thing that we just discussed, and also the same relevant code I've written over here. If you want to use the component way, you can use it with ECM component and ECM. Then this reads the value, then this stores the value in origin, and then origin, once we have stored in the origin, then it's going to onto the trajectory, and then we convert into the world pose. Once we have the world pose, we check if we add our the current target as our target. So basically this is the current waypoint, so we use the current waypoint and add it on the target world variable. Now this is the direction calculation that I just told you. This is the vector on the direction, and everything is same, and I've added some prints over here. Now it checks if it is less than this distance, then it is going to update this parameter. And the way this is implemented is it's going to make sure that it just rotates between 1 to 4. So what is going to happen is it is going to loop from 1 to 4, then 4 to 1. It's going to loop like this. Okay, so it's going to keep on looping. So this is for that reason is over here. Then direction normalizes it. It should never trigger, otherwise something is very wrong. Then stale delta t and the step. We are using our speed multiply with delta t, and speed is coming from this speed that we just saw, the speed, and based on that speed we are going to decide our step size. Will it be a bigger, will it be smaller? And based on that, every calculation that we just discussed, that z offset, yaw offset, and then we just apply our code over here, and then we do inverse, and we got the trajectory command that we want to send it up. And I've added the ECM way to make it happen, so you can read this as well, but I'm using the actor wrapper class. Then we send it to notify, and then there are some common prints, and then your registers. So this is the simple code. It's not difficult. Okay, this is not difficult, but now when we start seeing it working, it would look very nice. Okay, so let's try with this dog walk first. Okay, now let's launch our, have to show set first, and I've already kept it build, and then the animal, we have to manually write it. Launch file animal actor follow waypoints.sd.py. And interesting thing, I forgot to tell you this. So on the launch file, now I've added one more thing on the launch file as well. So this animal actor plugin, I've added this one more variable sim gz sim resource part. So this is basically to load where all of your models are there, where all these models are stored. These two models are there, so it just gets you the current path and model path, so that if you do not give this, then your model will not load. For that reason, I have added this up, and then this launches up the launch file. The same thing like we had it for getting the plugin path, same we have it for getting the model path. Now as we launch it, you'll be able to see this. See how well our dog is moving. So see, this dog is moving. So what we are doing, we are just making it follow this position. So we have given one target, and it is following those waypoints, and it is moving very decent because of the speed that I've tuned over here. All those values that are there. So here you will get the prints as well, so which waypoint it is currently at. If you want, you can turn them up, but I've put them so that we can see. So whenever it reaches the point, that it takes a turn very fast, and then which waypoint it has reached, what is the position. So it is a waypoint number 3. Now once it reaches the end point of it, now it's at waypoint 3 out of 4. Now it reached to waypoint number 0. So this is how it keeps on rotating between 4 waypoints. Okay, because and it's reading those values from here, and based on how you have tuned it, it is going to work like this. So now let me show what actually happens with the other one as well. And we'll see changing up sub parameter, and we'll see how this affect the entire motion of dog. So this is one another puppy walk. The SDF file is over here of puppy walk. So this is the SDF file. It's the same DAE file, and similar way I've created using Blender as well. Okay, now let's launch the scene once again. We need to comment this entirely. My bad, I should have commented this entirely. Now this entire is commented out, clear, and let's launch it. And this is the puppy scene. That's puppy keeps on walking on this surface. And this is running also slow, right? Because it's running at 0.1 speed. Now let me show you. If I make this yaw value 0 instead of 1, if I make this yaw value 0 and I make this velocity maybe 1.0, then you will start seeing it very odd. It won't behave like it should be, because the animation should match. Like, see, this is going this direction, and because this is an offset, that's what Z handles. Still, even if we make it again 1.57, because this is running with a very high speed, it is going to slide now. So what animation does, it just keeps on moving at one place, and we are just making it move. Still, you do not see it happening too much, but you'll see at some moment it just slides. It's not moving. You can see easily that it's sliding up, because you're running more faster than you should be running it at. And while recording, I actually recorded the animation at 100 milliseconds. So that's because of that, you need to somewhere match it within those limits, otherwise it's going to look very odd. And then this is Z offset. So the problem was, when I first wrote the code, the initial position value that you put on is just for initial. Once you start playing around this waypoint, then your Z offset robot was going inside the scene. So because of that, I made it work. I can make it 0 and show you as well. So these are small things, and you'll able to make one amazing walking or moving robot. Even though the robot was initially at this point, but once this plugin started moving it, it just went inside. To handle that, we have these values. So we are doing nothing, we are just making it follow waypoints. Okay, so that's the thing that you need to understand. So hope this logic of how making this cool plugin works is very clear to you, and I hope now you understand how to make things works. Whether it's animation or whether it's any other system plugin, you need to understand, and you have to see some codes that's available in the Gazebo Sim repository, and using those you can make your own scenes, and you can do so many crazy things, and you can make more interesting things that you want to make in Gazebo Sim. And you can use this custom plugin logic that entirely we talked about in the entire series. You can make it happen with your code.